Hello physics students. In this video, we're going to be performing an experiment testing the law of conservation of energy. So at this point, you should have already printed out pages 3 and 4 of the lab. These pages you'll be doing your analysis on and answering your questions. Pages 1 and 2 are just the instructions. So you only need to print those out if you feel it would be more convenient for you to read the instructions off of paper rather than off a screen. So what we're going to be doing is, if you look at the instructions, we're going to be testing that energy is conserved for pendulum like this. And so remember when we studied energy conservation in the video, I said that solving energy conservation problems, you had to ask yourself 3 questions in the beginning and 3 questions in the end. And all about energy. What kinds of energy does it have in the beginning? What does it have at the end? And then since energy is conserved, you set the beginning equal to the end energies. So for the pendulum, if we lift this up like this, we ask ourselves those 3 questions. Does it have PE spring? No, there's no spring here. Does it have PEG? Yes. How do you know? You can look up the formula, and the formula says that if you have M, G, and H that are not 0, you have PEG. So here we have this pendulum up high, and it's able to fall down, so we have PEG. Do we have the third energy, kinetic? No. Because I'm holding it in my hand, and kinetic energy is 1/2 mv squared, with v equal to 0, we have 0 kinetic energy. So when I let this go, it swings down to the bottom, and then we ask ourselves the same 3 questions. Does it have PEG down here? No, because if we set this equal to H equals 0, we could say that there's no PEG. Still no spring energy because there's no spring involved. But does it have kinetic energy? The answer is yes, because it's swinging down here. So kinetic here was the only yes answer we had, and PEG was the only yes answer we had over here. So we set those equal to each other. They should, according to the law, be equal. So what we're going to be doing in this experiment is calculating one, calculating the other, and seeing how close we get. Now the PEG part, that's easier to determine because the mass of this is known. It's 200 grams or 0.2 kilograms. G is 9.8, and the height we can just measure from a meter stick. And exactly how, I'll talk more about that later. So, but the point is we have everything we need right here to determine PEG. The kinetic energy on the bottom, though, is trickier because we need the speed down here. And what we've used for speed and acceleration so far in terms of digital equipment is we use the motion detector. And because this mass is so small and it swings in and out of view, the motion detector doesn't work well at all. In fact, it would not give us any meaningful data. So that we can put away. So the next thing that we can use is just V equals D over T. So that's why in step 1, we need to measure the diameter of the mass. So I'm going to go ahead and measure that. And what I'm just doing is, actually a ruler works better, is I am just holding the ruler up like this to the mass and just measuring across. And for me, what I get with this mass is about 2.73 centimeters, but you're going to look up on the Google sheet your own diameter. Everyone's going to be assigned a different diameter. I'll just jot mine down, 2.73 centimeters, which we always need in meters. So I'll go ahead and make that conversion. So you're going to look up on, like I said, the spreadsheet that I'm going to include in the stream, and you'll get your diameter right there. Now, the time when this swings down. Rather than read the procedure, I'm going to sort of talk about the theory of how I'm going to do this. So let's suppose I swing this down after bringing it to a careful height. And so maybe I try and use a stopwatch. What I'm going to do is I can't time it, start timing here because it's still accelerating. So I can only time it in a place where it's no longer accelerating when it's down at the bottom here. So let's suppose I put like a starting point and a stopping point, like the beginning of this meter stick and the end of the meter stick. And then I swing this down and I'm all ready to time it and I go. It's so fast, the mass going from here to here, the stopwatch is completely incapable of measuring that small amount of time. When I hand stopwatches out for an experiment, a lot of students play this game where they go and they see who can get the smallest number. And most students can't even get smaller than 0.1. Your fingers are not fast enough. And the time we're trying to measure from here to here is even smaller than 0.1. So a stopwatch with human fingers and human eyes and reaction time also useless for this experiment. We need a way to measure the time of this down here even more accurately. So what we're going to use is a device called a photogate. A photogate is basically this little device, and coming out of this hole right here is an infrared beam. It's like a laser that you can't see. And there's a detector on this side receiving that infrared beam. It's kind of like your garage door has a little safety, or it should, when the door's coming down, and if you put your foot into the path of the garage door, there's a beam there that gets interrupted, and the garage door knows to stop so it doesn't crush anybody. So that's what we have here, this little beam. And what it does is you could see that it detects when the beam is crossed. You see that light come on? And then when the light goes off, the beam is open again. So every time it's blocked, it can register the time. Every time it's unblocked, it can register the time also. And it can measure very small times. Watch what happens. See, when I put my finger through, the light flashed for a split second. I could never go that fast with my hands, but this can detect tiny, tiny increments of time. We're going to use that in this experiment by putting it down here and allowing this to swing through, and then it'll time the mass going through it. So in order to do that, I have to set up first the calculator to read that time. So let me turn on the calculator and configure it to measure the time as we need it in this experiment. Okay, so let me start the program. We need to give it a moment to establish communication between the calculator and the Lab Pro. Okay, so now what we have to do is set up this timing device to measure in the correct fashion what's suitable for this experiment. So what I'm going to do is go to this menu, Setup and Timing. And then it gives me two choices. I could actually run two photo gates here, but I'm only running one. So I'm going to turn that one on, and my choices are here of how I'm going to set up my timing. What I want is the first option, BL/UB. What that means is the photo gate will start timing the moment the beam gets crossed and stop timing the moment the beam becomes unblocked. So it'll start and stop. So let me do that, and then I'll show you why that's suitable for this experiment. Okay, so enter. And now I'm going to start data collection, and it'll make a beep. So watch when I cross this and close the beam, it's timing now. About 2-3 seconds, and there it is. So it times how long the beam remains blocked for. If I go like this, the time is very small because it began when my finger touched the beam and ended when my finger came out of the beam. So the reason why I set up like that is because this mass is going to swing down, and we want it to start timing when the beam gets first crossed by the diameter of the mass, and then to stop when it becomes uncrossed. So it's going to be a very small time like that from here to there. And we should see a very small time when we swing this down. All right, so let me clear this data and set the experiment up to collect our data. Okay, so I've got the photogate and calculator set up together to record the time as I just described. So what I'm going to do now is I'm going to put this photogate at the bottom of this mass's arc so that it can get the speed right at the bottom here. So now at this point, I've done all of step 3 and I'm on to step 4 of the procedure. So what I'm going to do is step 4 says lift the mass so that it raises up 20 centimeters. And then in parentheses it says it will not be 20 centimeters above the table. It needs to be 20 centimeters from the above its lowest position. How do you achieve that? So I want it 20 centimeters above here. What I'm going to do then is I'm going to measure how high it is down here. It's about 3.8 centimeters. So if I want it 20 centimeters above this point, I've got to lift it to 20 plus 3.8 or 23.8 centimeters. So let me do that now. All right, so there it is, 23.8. Step 5 says drop it through the photogate and catch it to prevent it from going back down through the photogate after it reaches maximum height. So what I have is 23.8 right here. I'm going to let it go and allow it to pass through the photogate and stop it before it comes back down. So I've got a time here. Let's take a look. As you can see, a time appeared here, 0.01390. So that I jot down in my data sheet right here, 0.01390 seconds. But remember, you're not writing this down. You're going to look up in the spreadsheet that I'm going to include in the stream for your assigned time for this experiment. Okay, so believe it or not, that's it for the data collection. Here's my data. Again, you're going to have your own that you find in the Google Stream in a sheet that I'm going to include. Everyone's going to have their own diameter and their own time. All right, so we're on to step 8 of the procedure. So here's what step 8 says. It says calculate the speed of the pendulum as it passes through the photogate. So there's a formula for calculating speed, a basic formula on the reference table in the mechanics section. I'm not going to tell you what it is, but basically it involves a distance and a time. Now a time we have right here, again, you'll have your own. So the question is, what distance do I use in step number 8? And there are, at this point, several distances. So time, all right, check. We've got that assigned. The distance, we've got 20 centimeters, which is 0.20 meters. We've got at the bottom, the mass was 3.8 centimeters above the table, which is that many meters. Or we've got the total height above the table, which is these two combined, 23.8 centimeters, or that many meters. And we have the diameter. So we have 4 different distances to pick from. It's only one of those. Again, you have to think about how this photogate actually worked, okay? So remember, here's the photogate, and the mass, when it came down, how did it start timing? When did it stop timing? And so that's what it timed for, passing through this photogate. So think about which of these distances would apply to the time that the photogate measured. So once you calculate the speed here, let's say you've got V equals and then something meters per second, right? So you got a velocity here. Now we're on to step number 9. Step number 9 says calculate the PEG before the release relative to the position of the pendulum at the bottom of the swing. So there's a formula for that on the reference table. So you're going to start with that. And then, I don't know if you could read this, but it says 200 grams. That goes into the formula, but keep in mind, it's in grams. So number 9, 200 grams somehow goes into that formula, but you have to do something with this before you plug it in. And I won't tell you what, but you should know that you have to change that somehow before you plug it in. And also, there's the height that goes into the formula. Again, we've got 4 choices for the H to plug into the formula. We've got 0.20 meters, 0.038 meters, the combined of those two, the total distance it was above the table, or the diameter. It's only one of those that's correct. You have to decide. Think about how a pendulum works and how potential energy gravitation works, and figure out the right one of these to plug into the formula. Okay, so that's going to be PEG here, calculated out. Okay. We move on to step number 10. Step number 10 in the procedure says, predict the kinetic energy at the bottom of the swing. Predict kinetic energy at the bottom of the swing. There's number 10. Predict means you're not calculating, but it also doesn't mean you get your crystal ball out and make a prediction like a fortune teller. It means you're using some idea we learned in physics that allows us to predict the kinetic energy. Think about the main idea of this lab, as well as what you've already calculated in the lab, and then write down a number here. There is definitely one right answer here. It's not like a prediction, so it could be whatever you want. It's either right or wrong based on what you already calculated in the lab. Okay, so KE here. On to step 11. Step 11, let me go like this maybe. You go to the procedure, it says calculate the kinetic energy of the bottom at the bottom of the swing using the speed you calculated in step 8. So we've got a speed over here, and then over here you're going to calculate the kinetic energy, nice format and everything, and have KE equals something here. Okay, so go ahead and do that now. Step 12, state whether your results show that energy was gained or lost in the experiment. How can you tell? Well, you look at energy before and energy after, and you see if energy was gained or lost. So write gained or lost right there, based on your results. Step 13, calculate the gain or loss. So how would you figure out from your numbers of energy what the gain or loss is? Go ahead and calculate it here. Gain or loss, write out the word gain or loss equals and then some number. Go ahead and do that now, one or the other. And then 14, calculate the percent error between the PEG and kinetic. The PEG is the accepted value. So go ahead and calculate the percent error there. Okay, so the rest of the experiment is questions. This one explain, and then this one is a series of calculations for, it's just like basically a homework problem right here about energy in a pendulum. Well, that concludes this lab video. As usual, turn in photos of your analysis and the answers to your questions in the Google Classroom stream, and I'll see you in the next physics video.